Long QT syndrome is a disorder of the heart's electrical activity, which left untreated can be fatal. Affecting 1 in every 2,000 people in the UK and around 1 million people worldwide, the syndrome is considered rare, often with no physical symptoms at all. The disorder leads to interruptions to the heart's rhythm. People with the syndrome find their hearts beat uncontrollably fast, which can lead to blackout or seizures. When an episode occurs, blood is not correctly pumped around the body, starving the brain of oxygen, resulting in fainting. Within a few minutes, the heart's rhythm returns to normal. The heart ECG is broken down into a number of sections: P, Q, R, S, and T. In long QT syndrome, the interval between Q and T is extended, leading to interruption in the heart's rhythm. Certain stressors are prone to induce episodes in people with long QT syndrome. Intense exercise, like running or rowing, as well as slow heart rate during sleep, are major triggers for an episode. But in the event that abnormal heart rhythm persists, the heart can contract irregularly and can stop pumping altogether, leading to cardiac arrest and death.
Ion channels are ultimately responsible for developing the heart's rhythm or its beat. This begins at the cellular level. On the surface of every muscle cell in the heart, there are pores called ion channels. It is these ion channels that can open and close to allow sodium, calcium, and potassium ions that are electrically charged to flow in and out of the cells. Each of these channels is just the right shape and size for the corresponding ion to fit through. For instance, a potassium ion can fit perfectly through a potassium channel. A sodium ion can fit perfectly through a sodium channel. However, a potassium ion is incapable of passing through a sodium channel, and a sodium ion cannot pass through a potassium channel. The movement of these ions into and out of the cell is what causes the electrical activity in the heart. This then spreads across the cells in the heart from top to bottom, making the heart contract and pump blood.
The hERG potassium channel, or human ether agogo channel, is responsible for the length of the QT interval. When the channel is blocked, potassium ions are delayed from leaving the heart muscle. Around 15 years ago, it was found that certain pharmaceutical drugs were causing blockage of the current. A typical example would be the antibiotic erythromycin, used to treat common infections like bronchitis or bacterial pneumonia. Due to this, all new drugs are tested to see if they block hERG. It is not known if this current is formed by hERG alone. However, it is established that these pharmaceuticals bind to hERG's pore region to block the current. Researchers at the University of Southampton are now interested in looking at what part of the pore is responsible for this blockage.
So if you take like a classical small molecule therapy which is being developed in the pharmaceutical companies, typically what you're looking at is a drug development process in the range of 10 to 12 years. So if we can start to understand the structural pharmacology of these integral membrane proteins at a very early stage, what we can do is, instead of just screening huge libraries, is we can start to feed in the structural information we have so that we can undertake a more rational approach to the design of drugs. If we're lucky, we may be able to save 4 or 5 years on the time it takes to basically, from the identification of a drug through to it coming to market.
The work currently ongoing at the University of Southampton is attempting to reduce the side effects of pharmaceutical drugs involving the hERG channel. This would mean that drugs developed in the future only hit their main target, rather than hitting additional targets, such as hERG, which may have harmful or even fatal effects.